Hello and welcome to this video where we're looking at motion graphs. So we're looking at displacement and velocity time graphs. So before we look at these two graphs in detail, I just need to remind you very quickly of two things that we can work out from a graph. The first one of these is the gradient, and that's often called the slope of a graph, but gradient is a better word, and the gradient is calculated by this. So we would find the difference in y divided by the difference in x. So what that means is we think about a starting point and a finishing point, and we look at the y coordinate of the finishing point. Well, in this case that's 20, that's equal to 20 minus the starting point, which was 0. So from going from here to here, the y values change from 0 to 20. So we're looking at how much the y values change. We divide it by how much the x values change. Well, they went from 0 to 10. So we do 10 minus 0. 10 minus 0. So basically we've got 20 divided by 10, which would give us a gradient of 2. And you can do that for part of the graph, you can do it for all of the line. If the line kind of went up and then went horizontal, you could work out the gradient of just the first sloping part of the line. The other thing we can work out from a graph is the area, and the area that we'll be interested in is the area between the line and between the x-axis. It's given different names, this area. Sometimes it's called the area under the curve. So although this is a straight line, it's often referred to as a curve because in general it can be any shape it wants. The area under the line, the area between the curve and the x-axis, all of those mean the same thing. They basically just mean all of this area that's between this line and the x-axis. We're not going to be asked to work out areas when our lines are actually curves. We're only really going to be interested in looking at areas that are rectangles and triangles because we can easily work those out. So let's start by having a look at displacement time graphs. Now, as we know, motion can easily be represented on graphs, and this is one of the two types of graphs that we most commonly see. Displacement is on the y-axis and time is on the x-axis, and we've got here three different situations. We can have very slightly different situations, but we'll look at these three. So if we look at this one, the displacement, the distance in a certain direction away from a certain point is staying the same all the time. So basically this thing is staying at 3 meters away from a certain point in a certain direction. So the only way you can do that is if you're staying still. So a horizontal line on a displacement time graph means that you are stationary, you're not moving. If we look at this graph, however, we can see that the displacement is changing. So you're starting off at a certain point, so you're 0 meters away from a certain point, and the distance or the displacement away from that point is getting bigger. So you're moving away from this particular point. But because it's a straight line, your displacement is changing by the same amount every second. So every second you're moving 2 meters, then another 2 meters to 4 meters, then another 2 meters to 6 meters, and so on. So you move the same amount of displacement each second. So this means you are moving at a constant velocity. So you have a velocity, it's not 0, but your velocity isn't changing. If your velocity does change, it looks like this because your displacement changes by, in this case, increasing amounts in each second. So if we look at this, after 4 seconds, we've moved 10 meters. After another 4 seconds, we've moved over 30 meters. So in this case, this person has sped up. So basically, they've accelerated. Obviously, there's two other things that could potentially happen. You could, if we go back to this graph, you could, for example, have a line that looks, for example, like this. And if that happens, then what's happening is you're still traveling at a constant velocity because really your line is straight. That's the important bit. If the line is straight on a displacement time graph, you're traveling at a constant velocity. But in this case, your velocity is negative, and you can tell that because it's sloping downwards. So the gradient is negative. And so therefore what we have here is this thing is going at constant velocity, but it's going backwards, it's going back towards its starting point until the displacement is 0. We could also, for example, have on here something that is travelling very fast and then slows down. And if that does happen, then what will happen is the displacement will change a lot every second, and then gradually the displacement per second will decrease. So if you're decelerating, you would end up with a graph that looks something like that. So we can have a quick look at what the gradient and what the area of these graphs actually represents in a slight bit more detail. So I'm going to consider the middle graph because that's kind of the easiest one to consider because it has a gradient. This one does have a gradient which is 0, but we'll consider this one simply because it's kind of easier to get our heads around a little bit. We saw at the beginning that the gradient is simply given by the difference in y divided by the difference in x, and our delta again means that that basically means difference. For this graph, a change in the y-axis actually represents a change in displacement, so we can write delta y as delta s, where s is our symbol for displacement. So a change in y actually really means a change in the displacement, and delta x means a change in the x-axis, and because this is a time axis, any change in the x-axis is representing a change in time. So in this equation, if we put in, instead of delta x and delta y, we put in what they represent, which is the change in displacement and the change in time, we end up with this equation over here. So the gradient is the change in displacement divided by the change in time, and as we saw in a previous video, this is equal to the velocity. So the velocity of this object is given by the gradient of this graph. Now you can also work out, if you could, for example, work out the gradient of this graph, and if you did that, the difference in displacement divided by the difference in time, well, the difference in displacement is 0 because it's the same all the time. And so a horizontal line basically means that your velocity is 0, because you would have 0 divided by 10 in this particular graph. Finding the velocity from this particular graph is really hard. Now, but what you could do, for example, is you might want to know the velocity at a certain point, because the velocity is changing, because we know that this thing is accelerating. So let's imagine that we wanted to know the velocity at 6 seconds. So what we would do then is we would draw a tangent to this particular curve at 6 seconds. So we draw a straight line with a ruler like that to this particular curve. Now, obviously it doesn't touch the whole curve because the curve curves, but a straight line, you draw a tangent to that particular curve, and then you would work out the gradient of that. And what that would tell you is the velocity at this particular time. You could then do it further up here or further down there, and because the gradient is changing, you'd end up with different velocities. But that's how you'd work out the velocity from this thing. Now, for displacement time graphs, the area under the curve means nothing whatsoever. It doesn't have any actual physical representation. So for displacement time graphs, you don't have to worry about the area. So if we look at velocity time graphs, we'll see that there are 3 graphs here. They look basically the same as our displacement time graphs. The only real difference between these 3 graphs is that we've replaced displacement on the y-axis with velocity on the y-axis. So we'll start off and we'll take each graph in turn to see what they represent. So here we've got a horizontal line, just like we did on our displacement time graph, but it means something completely different. In this case, what's happening is the velocity is always 4 meters per second. So basically what that's saying is that this person or this object is traveling at 4 meters per second all the time. It's not getting faster, it's not getting slower. So it's not accelerating, but it is moving. That means that this thing is moving at constant velocity. So its velocity remains constant or remains uniform. If we look at this, however, what we see is that we're starting off at basically 0 velocity and small velocities over here, and we finish up with much bigger velocities of 30 meters per second over here. So what's happened here is our velocity has increased, it's got faster, and so therefore what this means is that this thing accelerates. Now, because the change in velocity every second is the same, what that means is that we've got constant or uniform acceleration. So this thing is accelerating, but the acceleration is a constant. It's not changing. So velocity increases, but the rate at which the velocity increases stays the same. This third graph shows what happens when acceleration itself changes. So here we're starting off at small velocities, and here we've got a velocity that's changing, but only by a small amount every second. Whereas here, the change per second of the velocity is much, much bigger. So here we've got small acceleration because the velocity only changes by a small amount every second. And here we've got bigger acceleration because the velocity changes by large amounts every second. So what's happening here is that this object is accelerating all of the time, but we've got non-constant, basically, or non-uniform acceleration. We've got small acceleration here and bigger acceleration over here. So we can have a look at what the gradient and the area in this case represents. So again, we'll go back to this graph here, and we can see that in this particular case, when we're thinking about the gradient again is the change in y is the change in velocity. The change in x, in the same as it was on our displacement time graph, represents a change in time. So like we did before, we can replace the delta y and the delta x with delta v and delta t. Delta v and delta t, basically you've got a change in velocity divided by a change in time. If you actually calculate that, it gives you acceleration. So in this case, the gradient of this graph gives you the acceleration. If you want to know the acceleration, at some point on this graph, you do the same as we did before. You draw a tangent and calculate the gradient of that tangent, and that will tell you what the acceleration is at that particular point in time. If we think about the area, it's potentially easier to think about this graph over here. So the area for this particular rectangle is simply the base multiplied by the height. And that gives you the area of the rectangle that's below this line over here. Now, if the base is this distance over here, which actually represents the time, the height of this rectangle up here represents the velocity. So what we're really doing is velocity times time. So if we do that, we think about this thing. If we go back to our equation for velocity, velocity is equal to the displacement over the time. If we rearrange this equation, so we get velocity times time by multiplying both sides by t, velocity multiplied by time is equal to s, so it's equal to the displacement. So what the area of a velocity time graph gives us is it gives us the displacement, or it gives us the total displacement that this thing's travelled. So if we want to know the displacement after 10 seconds, we'd work out this full area of this rectangle. If we wanted to know the displacement after 5 seconds, what we do is we draw a little line down here like this, and we just consider the area of this shape here. So the area of this shape just gives us how much the displacement is in meters after 5 seconds. So the difference with velocity time graphs, and well, I suppose it happens on displacement time graphs as well, but it's more common on velocity time graphs, again, is what happens if our slope is negative. But we're going to think about velocity time graphs because this can mean something that's important. So what this shows is to start off with, is that our velocity is decreasing. So it's starting off at 5 meters per second and it's gradually going down until it gets, after 5 seconds, it gets to 0. So at this point, it's instantaneously stopped. Now it then becomes negative. So what's happened is our object is moving in this direction, but it's gradually slowing down until it gets to a certain point where it's stopped. And at this point, its velocity is 0 meters per second. But that's not the end of the story. It then starts to have a negative velocity, which basically means it then starts to move backwards. So this line represents moving forwards, but slower, getting slower, stopping, and then turning around and getting faster and faster, but in the opposite direction to the direction that it started to before. So we're going to have a look at one worked example that kind of embodies all of these types of things, and we're going to look specifically at a velocity time graph. So we've got a tennis ball and it's thrown vertically downwards with a speed of 1 meters per second. So we're starting off with a ball here and somebody throws it downwards at a speed of 1 meter per second. It then bounces on the floor and it's caught again. So it goes down, hits the floor, and then bounces back up again. When it hits the floor, it's travelling at 3.5 meters per second. So just as it hits the floor, so the speed just before it hits the floor is 3.5 meters per second. Here, we want to sketch on this velocity time graph basically this motion. Okay, so we're asked to, on these particular axes, sketch a velocity time graph for the ball from the moment it's thrown downwards to the time it's caught again. And we're told that the ball bounces after 0.25 seconds of being thrown. The initial velocity is marked here, and the final velocity is marked here. Okay, so we then have to work out what this velocity time graph looks like. So there's a couple of things that are really important here. First of all, we're told the initial velocity. Well, the initial velocity is minus 1 meters per second. So what that tells us is that whoever started to draw this graph has basically decided that a downwards direction is negative, so the upwards direction must be positive. And what we're then told is it starts off with a speed of 1 meter per second, so that's why the mark is here, but it finishes off with a speed of 3.5 meters per second. So in other words, just before it hits the floor at 0.25 meters per second, it's finished up at a speed of 3.5 meters per second. But because that's in a downward direction, the velocity is minus 3.5 meters per second. So in other words, it finishes up here. So then what we could do is we would take a ruler normally, and we would draw a straight line that goes down there like that. Then it becomes a little bit more complicated because we have to think about what's going on. So what's happened is this is speeded up in a downwards direction. When it hits the floor though, it starts to move upwards, and it moves upwards, so therefore the velocity suddenly becomes positive. So it goes down, 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 down. So it's negative, 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 hits the floor, suddenly becomes positive. So instead of the velocity now being down here, it's up here all of a sudden, simply because it's changed direction incredibly quickly. Now, there's an extra bit here that we've not really looked at, but what's important for this is falling downwards, and gravity is the thing that makes it fall downwards, and gravity is always a constant acceleration. So the acceleration for the falling object, or for the object moving upwards, is always the same. So acceleration is the same. What that tells us is that the slope of this graph is always going to be the same no matter where this ball is. So what we can do is we can basically say, okay, so the finishing position is here. I can work my way backwards simply by saying that the gradient of this line must be equal to the gradient of this line, and I'll do my best to draw a gradient that's approximately the same. So that would do that like that. So that's basically what our graph looks like. We've got this thing here where it's speeding up until it hits the floor, and then it hits the floor and the direction suddenly changes, and then as it moves upwards it slows down because it's accelerating towards the floor, but it's moving upwards, so it slows down until it gets to its final position. So that's the first part of this particular thing. We're then asked for part B and for part C to calculate the acceleration of the ball and the initial height that the ball was dropped from. And I've tidied up my graph a little bit, so you've actually got some straight lines. So first of all, we're looking at the acceleration of the ball. So what I need to do for that is need to write down my equation. So my equation for my acceleration is this equation. So it's the change in velocity divided by the change in time. So if you remember, this is the final velocity. So this is the velocity that the ball will finish with, final velocity. This is the initial velocity, or the starting velocity it starts off with. So that's initial velocity. And this is simply the time. So I need my final velocity. Well, as it's dropping down, just before it hits the floor, my final velocity will be 3.5 meters per second. So A is equal to, actually, so it's 3.5 meters per second, but because it's going downwards, it's minus. So my final velocity is minus 3.5 meters per second. I then take away my initial velocity. Well, my initial velocity was 1 meter, the speed was 1 meter per second, but it was travelling downwards again, so my initial velocity was minus 1 meter per second. And I divide that by the time, and we're told it took 0.25 seconds. And if I do that on my calculator, I end up with minus 2.5 on the top divided by 0.25 on the bottom, and if I do that, I basically end up with a value of minus 10 meters per second squared. So the minus simply means it's acting in a downwards direction, and the magnitude of this vector is 10 meters per second squared. So that is basically the acceleration due to gravity to one significant figure. Finally, we're asked to calculate the initial height that the ball was dropped from. So we'll move on to a different screen. The initial height the ball was dropped from is so height, or distance, or displacement, is simply represented by the area between the curve and the x-axis. So we're thinking about the height it was initially dropped from, so we're thinking about this part of the motion here. So what we want is we want to know the area of this part here. So if we get rid of those lines, what we're going to do is we're going to separate this area into two bits. So we're going to draw this line across here like this. So what I've actually got is I've got a rectangle like that, and I've also got a triangle that's got that type of shape. And I use my numbers that are on the axes. So for my rectangle, the distance between there and there we're going to take is to be 1. The distance from there to there is 0.25. For our triangle, the distance from here to here is 0.25 again, and the height of my triangle is the height or the distance from there to there. So it's minus 1 to minus 3.5. So that's 2.5. So I just now simply need to work out the areas of these things. The area of this one is really simple. It's just 1 times 0.25. So the area of this one is 0.25. The area for this one is slightly more complicated, but not a lot really. It's a triangle, so the formula for the area of a triangle is simply half base times height, so that's a half times 0.25 times 2.5, and so if I do that on my calculator, I get 0.3125. Now my final height, in other words, the distance it was dropped from, is simply the whole area. So I add that area and that area together. So my height altogether is simply the two areas added together. And if I do that, I get 0.5625 meters, which is equal to 0.56 meters to two significant figures. And I've chosen two significant figures because the values in the question are given to two significant figures. Now, you might well be wondering why I didn't choose to use -1 and minus 2.5 over here. If I was asked for the displacement, I would do that because displacement is a vector, and so you'd have to consider the signs of these things. Because I'm just asked for the height that the thing was at, that's basically a distance really. So we just want to know how high the ball was before it was thrown downwards. So I was a bit lax in a way, and I just decided that I was going to work out the distance rather than the displacement. Okay, so that's motion time graphs, that's distance and velocity time graphs. It might be worth going back and just making a note of what all the quantities on your two graphs look like, because although they're actually fairly simple, sometimes you can get questions like this that are quite in depth. Okay, so that's it from me. Thank you very much for watching.